Hi, everybody. My name is Ahmed Garces. I'm a third-year master's student at the MD Anderson UT Health Graduate School of Biomedical Sciences, and today I'm here to talk to you about combining proton therapy with IDH1 arbor-32H inhibitors to treat glioma stem cells. Now, first to start out, malignant glioma is the most common form of primary brain cancer in the United States to date, and these tumors, when they come to the clinic, are given a grade from a scale of 1 to 4 based on histopathological and genomic analysis. Grade 1 tumors are considered the most benign, while grade 4 are the most malignant and are defined as glioblastoma multiforme. Now, within glioblastoma multiforme, or GBM, there's two different flavors, primary and secondary. Primary GBM tumors develop de novo, primarily in elderly patients, and constitute 90% of all cases of GBM. Secondary GBMs develop mainly younger adult patients and constitute the malignant transformation of low-grade glioma, otherwise known as grade 2, all the way up to a glioblastoma multiforme, and constitute 10% of GBM cases. Now, we're going to be focusing on lower grade gliomas for the sake of this presentation due to their unique genetic profile that offers opportunities for therapeutic intervention. Now, what I mean by that is that most low grade gliomas harbor mutations in IDH1 arbor-32H, which has been shown to impair DNA damage repair via homologous recombination. Additionally, astrocytomas have been shown to show loss of the ATRX chromatin remodeling protein, and this has been shown to impair non-homologous end joining DNA damage repair. Now, when we're defining novel therapeutic modalities based on these genomic alterations, it's important to keep in mind that the tumor itself is constituted of the tumor mass as well as the glioma stem cell population, which is a self-renewable cancer stem cell population that promotes chemoradiation resistance as well as secondary tumor genesis, and is extremely important to eradicate along with the rest of the tumor mass. Now, the two current treatment modalities that we have for treating gliomas that I'm going to be focusing on today are proton radiation therapy and IDH1 arbor-32H inhibitors. Proton therapy is a highly tumor-specific and more effective at inducing double-strand DNA damage compared to conventional X-ray therapy. IDH1 arbor-32H is a novel treatment modality that is used to inhibit the IDH1 arbor-32H function, inhibits 2-hydroxyglutarate production, as well as has been shown to impair tumor growth in vivo. However, the combination of these two modalities has yet to be discovered in the literature. And so we believe that combining these two treatment modalities will actually not synergize, and ultimately promote self-renewal of glioma stem cells. As you can see right here in the methods, the way that we quantified self-renewal was through the limiting dilution analysis. We seeded single cell suspension of GSCs at different seeding densities, irradiated with a combination of inhibitor, and counted the number of wells that formed spheroids compared to those that did not. As you can see right here, the results are shown in panel 1. So before I present my own data, I'm going to show in panel A a result from Molinar et al. In 2015. And they showed that actually combining ionizing radiation with IDH1 arbor-32H inhibitors, which is AGI 5198, actually promotes the clonogenic survival of glioblastoma cells. And we actually recapitulated these results using glioma stem cells and the self-renewal capacity assay, limiting dilution analysis assay, sorry. And you can see right here the results in panels B through D. The graphs show the log fraction of non-responding on the y-axis, the log fraction of non-responding wells compared to the dose of cells that was originally seeded in those wells. So the more towards the horizontal that the solid line tends towards, the more effective the treatment modality was at eliminating the GSC population. The more vertical it is, the less effective at the treatment modality was at eliminating the GSC population. So you can see right here, X-ray therapy compared to combining X-rays with ivosidenib in the MGG18 cell line was not nearly as effective. X-ray therapy is more effective than combining the two treatment modalities. And we saw the same thing with proton therapy in both the MGG18 cell line and TS603 cell line, both of which harbor IDH1 arbor-32H only. It's worth noting that in the panel C, proton therapy combined with ivosidenib, although it showed a non-significant result, this is actually important because we showed that either there is no significant benefit to adding these inhibitors with radiation, or that they actually promote self-renewal capacity of GSCs. So to follow up on these results, we go to panel 2 right here, and we could recapitulate these results in a cell line that has both ATRX loss and IDH1 arbor-32H, the same genetic profile that astrocytoma patients harbor. And so we saw the same results using proton therapy and ivosidenib, and proton therapy with vorasidenib, two distinct IDH1 arbor-32H inhibitors. And so we show that ATRX loss is not enough to resensitize the cells to the effects of proton therapy when in the presence of IDH1 arbor-32H inhibitors. And so you can see right here in our discussion section that combining radiation therapy with these inhibitors of IDH1 arbor-32H is not effective in in treating the GSE population and ultimately could end up harming the patient in the long run. And so our future directions is to continue investigating this trend in GS522s, which is another ATRX loss IDH1 R132H cell line, as well as to quantify apoptosis, necrosis, and DNA damage repair of the combination modality.